Hi guys, Mr. Bennett here. Today I just want to look at the investigation you've got to do for integration. Obviously we're working with areas under the curve, and one of the key things that we need to look at there is trying to model a curved shape. So obviously the most basic curve shape is a circle. So what you'll find here is when we start looking at this function here, that function there, what we're looking at is part of a circle. Not the whole circle. It's a quadrant of the circle with a radius of, this one has got a radius of 3. So then if we were integrating from -3 to 3, that will give us a particular thing. Now if we start looking at the formula for a circle, for a sphere, then if you did the integration of that from the -3 to 3 of this function here, and you compared that with what you're going to get if you basically just use your formula for a sphere, which is 4/3 pi cubed. Now the formula we're trying to show is this one here. Okay, the volume is equal to pi -a to a of a squared take x squared squared. Alright, so this is what we're looking to try and show in this first one. So if we can prove what we do normally when we were working at the volume of a sphere with the integration, and the idea of this particular shape being rotated 360 around that way, then that is really what we're trying to show. Now the first shape, that's the first shape that we've got, so we're going to try and prove that that is f of x squared. Okay, so and then we're talking about if that works for the circle, then it possibly will work for any polynomial. Now my suggestion for this, we've just extended it a little bit further. This is looking at a little bit more difficult sort of shape. So this is basically two cones that are stuck along the base. The base there has got a base of 10 radius, and it's got a height, one's got a height of 5, the other one's got a height of 2, and so therefore we've got two cones that are stuck together there. If we rotate that shape around 360, then that's actually going to produce a volume of a shape. Alright, so, and we're going to try and prove that that as also works, that formula that we've got above works for this particular shape as well. To help you, we're giving you the formulas for those, and so therefore we have to show that's basically what we're doing there. So you need to do the integration, show the steps there, and then find the volume and prove the volume of two cones, and this particular volume are the same. Now, it doesn't ask you to do that, anything more than that, but what I would probably be thinking of is, does it work for other multiple shapes? So this one here, I'm thinking of a cone, not a cone, a cylinder, with two semi-spheres on the end. Okay, so if you did that sort of shape, how would that go? You could look at a cylinder with a cone like on the top. Alright, so see if it works for that particular shape. And then what you might want to do is you might want to say, does this work for non-circular shapes? So if we have something like a box followed by a square-based pyramid on the top, would that work? Okay, now that might be the proof that it doesn't work for these particular shapes, so that might be worthwhile doing. So it's only going to work for shapes which actually, when they rotate, produce basically a circular shape. And I think that's really what we want to prove there. So you might want to use an example of something like this to show that it doesn't work for all shapes that aren't basically circular. Alright, so that might be something worthwhile doing. Now you can put all of those particular values into a table, and then you can actually show the formula from the integral, and then from the formula itself, and you can actually compare which ones work. Alright, going to go up to part B. So part B is now choosing an object of your own. Alright, so obviously you need to be able to find the volume of your particular object using non-calculus as well as using the calculus method. So just assume that this formula that we found up here actually works. This formula is the one that we're using. So that's what we're going to do. We might need to look at a multi-shape particular object. Alright, so that's obviously a little bit more complex, but not much more complex. Now, if we come down to the steps that I think you need to follow, the following. So you need to get a picture of something. Alright, so here's an example of a sauce bottle. Alright, so here's my sauce bottle. So you need to obviously have a grid over the top. So you need to know obviously the length of something so you can have a scale for your grid. And then you've got to put your points. And then what I suggest you do is put these points into either GeoGebra or into Excel. Now Excel will allow you to find a model. Now with Excel, on your polynomial stuff, you can have different things. Alright, so if I come in, so here's my data, I'm going to insert a scatter graph for that. Okay, that's my curve there. So what I'd like to do is I'd like to represent my trend line, so I'm going to add a trend line. And what I'm going to do is display my equation, display my R² value. I'm going to choose a polynomial. Now you can either choose that to be a quadratic. Okay, if I do that, it'll give me a quadratic, which doesn't fit that well. Right, so you can try some different things. So if I now try and add a trend line again and do a polynomial, and you can format this. If I do a cubic, okay, you can see the cubic's going to match that a little bit better. Alright, and then you can probably even just, you can scale these in terms of having different color lines and different things there, so you can see the different functions. So you might even display it just on one graph. I can also, if I now go there, I can certainly add another high power polynomial. Alright, so if I do that, so I might go to the power of 5 and close. And you can see the one with the power of 5 is getting a lot closer to my function. Now, if we were looking at these particular functions, and we could do comparison for under the integral, so the key thing is your calculator will do the function for you. You don't need to do the integration. But if I'm actually showing that function there, which has got a higher R² value than the other one, which has only got an R² value of 8.4 roughly, and that's 9.99, I would think I'm getting a much closer volume. Alright, so I think you can try some different models there. That's what I'd be doing, and showing that, you know, obviously the higher power, the higher the polynomial, then the closer it's going to match the real data itself. Alright, so get the idea. So you use maybe Excel to do that, and then you can just put that into your graphics calculator, that function, and you can do your integration as shown. And the sort of thing that you might see when you go back to your calculator bit, alright, you might even just show that, I don't know, but I mean, you don't even have to show that part of it. Now, key thing is when you're trying to summarize stuff, you need to be putting things into tables. Alright, so now you need to think of ways of actually finding that. So you might actually fill your container up, put it in and pour it out into another container, and you can measure the volume. This person here looked at the submerging method. Alright, so again, if you're obviously going to submerge something, then you're going to you're looking at the overflow of water. The other method you might want to consider is if you've got like a glass or something like that, you may want to fill the glass up with water, or weigh the glass first and fill it up with water, because water, roughly, I think the density is 1 litre of water that weighs 1 kilogram. So that might be a way of doing that, because remember, when you're pouring water out, some of the water's going to stick to the side of the cup, so you're not going to get an exact measure. Anyway, you can talk about in your investigation the limitations of what you're doing there. Alright, so limitations and how you can improve things is a really important thing that you need to do with that. So like any investigation, you must go through and have obviously an introduction to about what your particular investigation is all about. Alright, you then need to show all your working out. So you need to summarize things in tables. You need to analyze your results as you go through. Certainly in this particular point, I'd be doing calculations for percentage errors, so I'd be showing the calculation for that, comparing your results that you got from your calculus method to what you actually get when you measure. Alright, so I'd be summarising information to tables. So you need to have a discussion about what the results tell you. Right, very, very important part. If you look at your performance standards, you need to obviously do modelling, and that's what we're doing here is we're modelling the stuff. We're using technology to do that, to make it more efficient. We are then also going to talk about the limitations of the sort of results that we're getting and how we might improve those results. You can even suggest things that you're not even going to do. Alright, so that's the other way. You don't have to always do things, but you can talk about how you might improve things. Certainly you need to talk about the possible sources of error and how that can be, how it can affect your overall results for that. But essentially, I think you should have a fair idea about what you've got to do. So you've got to pick, obviously, an object, do something that's really curvy. That will just make it a little bit easier to get your polynomial shape. And make sure then, once you've done all of that, once you've done your discussion, then you need to be writing a conclusion that talks about what you've discovered in the investigation. Alright, so obviously can't cover everything in the video, but I think this gives you a bit of an idea about what to do. So obviously if you need some more help, you need to catch me in class.